So good afternoon. I'm Dan Atkins. I'm an emeritus professor of information, electrical, and computer engineering. I had the privilege of being a faculty member and an academic administrator here for over 50 years, and I'm delighted to have this opportunity to come preside over this afternoon event. I want to begin by giving you a little background really relevant to the topic today and to the existence of this recently announced postdoc program. About 3 years ago, the National Academies, which is an organization in Washington that includes Academy of Science and Engineering and Medicine. It was founded by Abraham Lincoln and chartered by Congress. Very old, and it's intended to be a resource to the nation in science and engineering. And they do consensus studies on topics that various government agencies or private foundations wish to explore. They were approached by Eric Schmidt's Science Futures organization. Eric Schmidt, you know, was chairman of the board, maybe still is, of, no, not anymore, of Google, but a very wealthy individual who is using his money for innovation, investing in high-risk, high-payoff science activities. They asked the NSF the National Academies to conduct a study on topics of advanced and automated workflows enabled by the emergence of AI. Getting some feedback. I was asked to chair it, and I had the honor of doing that, and I worked with, what do I push to make this change? It worked a minute ago. With these people, who this is pro bono contributed lots of time over a 2-year period to the production of this report. And two of the panelists, people here, Tapio Schneider and Ike Altinas, are here today to share with you the work that they are doing in this area. And we also have with us today two people that attended a workshop where we gathered information about the state of these activities. And one Tim Cernak is here, professor of chemistry, and then we have online in a moment Alex Szalay, a very distinguished astronomer based in Johns Hopkins. So you are really getting the opportunity to interact with people that are literally on the leading edge of this activity. And also I'll point out that Al Hero, a faculty member in ECE, was also a member of this. I'm not going to go through all these slides in detail. You have either hard copies of them or links or PDFs that you can look at, but I just wanted to lay the groundwork. Now, the general topic that Schmidt is investing in is AI in science, meaningful use of AI in science, with the idea of the automated research workflow being an important, I would say, special case of that, or maybe the ultimate outcome of it. So the way these reports work is that you examine the current efforts. You have a workshop, an invitational workshop, to bring people from various perspectives together to try to gather the basic ingredients that goes into the workshops. And then you produce a report. And the report you all have, I believe, been given the link to, and I would encourage you to read it. So this is the report. And the idea of workflow is being used in a very broad sense. All of these different aspects of workflow are a part of it, and we were very non-prescriptive about the exact definition of workflows, and the report was definitely not an evaluation of the existing myriad workflow software systems. And the motivation for doing that was the widespread awareness of the transformative potential of AI, and we referenced one report that was getting a lot of attention at that time. The growing activity to apply AI in sciences, the significant progress in open science and open data, which is an important prerequisite, the report says, to the success of the ARW movement. The fast-growing contemporary lab books, which are things like Jupyter and so forth, we think may be on-ramps to these environments and starts down the path towards them. And the increasing challenges of reliable and reproducible research that hopefully these workflow systems can help alleviate. And very importantly, and you will hear some examples of this, the potential for dramatic acceleration of the exploratory loops in experimental work. Yeah, okay, I'll turn on my... Okay, good, thank you. So these are just the various panels and the way we kind of structured the workshop. And kind of like today, this workshop was going to be a face-to-face meeting in Washington, D.C. with about 150 people coming from all over the world. And, but COVID hit at that time. And so in very short notice, we converted it to all virtual. And it actually worked pretty well. We had working across 8 time zones for a day and a half. And so thank goodness Zoom was there just at the right time. But we didn't have any nice dinners and wine and so forth. The automated discovery loop, this is a model that one of our speakers proposed that goes into that. I'm not going to go through it. Tapio will talk more about it, but the main point I want to emphasize is, well, first off, that the notion of acceleration includes things such as acceleration of the generation of workflows, acceleration of exchange and reuse of workflows, and of course, acceleration of the workflow itself. So the notion of acceleration is somewhat broader than you might think. So the main thing I want to bring your attention are these examples, and there are many. There are 6 or so case studies, 2 of which will be alluded to today, 3 of which will be alluded to today. Material science, cutting the time required for synthesis from 9 months to 5 days. Particle physics, a given sensitivity using half the data. Drug discovery, finding 57% of the active compounds, performing 2.5% of the possible experiments. Astronomy, automating telescope target selection so that observations are optimally informative. Alex will talk more about this work in the context of astronomy. And a very interesting project we had from the UK where they were using AI methods to analyze enormous volumes of ancient manuscripts in a wide variety of ancient languages and extract trajectories of history and development of ideas and so forth. Something that one could never do depending purely upon human scholars. So this is a big deal and is going to be a big deal. And I think Michigan is in a pretty unique position together with maybe a few other universities to really seize a leadership role in that, and that's why I'm delighted that we have this attendance today and that we have these experts here to help us get our head around the opportunity space. So I won't go through all these findings and recommendations except to end with the fact that if you do a word cloud of the report, this is what it looks like. And with the central thing being both the enabler and requirement data. So I would argue this is a very appropriate topic to be centered in an institute of data science. So I'm not going to give long bios of our speakers. You can find them on the website. Just take my word for it, if I did them full justice, we'd be here at least an hour just to announce them. But they are the real thing, and again, we're very honored to have them. So without further ado, we're going to switch to Alex Szalay, who is joining us from his home near Johns Hopkins. I've had the privilege of working with Alex for many years. He's enormously generous with his time and expertise. He's also, I hope he doesn't embarrass, he is literally a rock star in his home country of Hungary. Amazing rock and roll guitarist who I envy enormously for that. Okay, Alex, take it away, please.
Yeah, thanks you very much for inviting me, and I'm sorry I can't be present there in person. So I would like to talk today about how these automated workflows are really creating a revolution, the next revolution in open data. And open data is altogether exploding exponentially, and this transforms everything in science and leading to a much better and more open science. And this is, of course, enabled by Moore's law, the exponential growth in our computational technologies. And I had the privilege over the years to work with Jim Gray of Microsoft and of Turing Prize Frame, who has worked with us, with astronomers and with the broader e-science community in establishing the importance of open data. And he tried to classify the different phases of science into the different paradigms. And science is changing exponentially. So we used to collect for thousands of years empirical data, you know, the Chinese star charts and Leonardo's codices captured the turbulent flows. Then eventually when Tycho Brahe shared his data about the motion of the planets with Kepler, then that led to Kepler's laws, a mathematical abstraction that led to the beginning of the theoretical branch of science, where we could take the empirical data and create, condense them into very simple analytic equations, which we could also solve. And this culminated in Einstein's general relativity. The equation on the right is the equation that governs the expansion of the universe. But we reached a point when, for example, we could write down the equation like the Navier-Stokes equations describing turbulence, but we couldn't solve them analytically. Even today, these equations don't have an analytic solution. And so this led to the emergence of the computational branch of science, where we used the emerging computers, and first in the Manhattan Project, to solve some of these partial differential equations. And so this led to a computational branch of the different sciences, to computational physics, computational chemistry, computational biology, and so on. But lately, we have seen the emergence of data-intensive science, where computers are an inherent part of the whole scientific process, and data permeates. So, and here we synthesize, this is convergence, and we synthesize theory, experiment, and computations with statistics. And this requires a new way of thinking. But when you look back, it took thousands of years to go through the first paradigm of science, a few hundred years on the theoretical. It took a few decades to go through the computational branch. And today, this is happening right in front of our eyes. Science itself is also changing how it is organized, how is it self-organizing. It all started in Oxford with the Department of Natural Philosophy, which eventually subdivided into physical sciences, life sciences, earth sciences. And then over the last century, we developed the theoretical, experimental, and computational sub-branches. But today, what we see is there is a convergence, as I mentioned before, which all these different disciplines they are not developing a data-intensive branch of biology or medicine. It turns out that the techniques of data science are actually quite similar in all the different disciplines. So they are kind of hanging on around this bigger cloud of data science, which in itself is an aggregation of computational science, computer science, statistics, mathematics. And so the data science is becoming the new math, the new shared language of science that everybody will have to acquire. And as a result, we need to change how we educate people. And so today, most of our higher education is training deep but very narrow people who are eye-shaped. So basically, they are vertical. And as we get older, then we tend to become T-shaped. So we develop a horizontal, broader, but very shallow branch where we can at least communicate with our colleagues in other disciplines. But what we need in this new world is to have basically people who are not just I-shaped or T-shaped, but they become pi-shaped, like the Greek letter pi, where we have to have a deep leg in our own scientific discipline, but we also have to grow a deep leg in data science. Otherwise, we will not be able to formulate or solve our problems. And we are right now at the cusp of a new change. New disciplines emerge when two domains intersect, like genomics emerged from the intersection of Watson and Crick interactions, where a physicist and an ornithologist got together to develop a new area of science. Here, basically, we need to fuse data science with our own disciplines. And scientists need to become pi-shaped and grow a deep leg in data science as well. And this is well on their way, because one just has to look at the attendance of the introductions. Sorry, can somebody, I'm getting a feedback on my voice. Yeah, thank you. So we need to train pi-shaped people in this new world. The granularity of science is changing as well. So science used to come, much of the scientific data used to come from manual production of scientific data in small scale lab experiments to the Industrial Revolution. And this change has happened in the middle of the 20th century. So before 1950, there were typically small experiments by few individuals, and the number of them was slowly growing and the experiments superseding each other. And in the 1960s, so after the World War, we started to get into big science, building large national laboratories, each of them costing billions of dollars, and some of the experiments took decades to build, and then another few decades to run. And typically, because by the sheer scale of it, they had to be very risk adverse, and if you involve thousands of people. This is a big difference. So in the past, with the small experiments, these rapidly followed one another, and data sets had a short life because the results were superseded very quickly. But with the big science experiments, which involve billions of dollars and the National Science Board approvals and so on, they are around in every discipline of science, but they may not be surpassed by another experiment of the same kind in our lifetime, simply because it takes so long to build one. And so when we look at, for example, the evolution of particle physics and nuclear physics, so we started out with the small-scale Van de Graaff generators, then Thomson built Cockcroft and Walton built the cyclotron in Cambridge. Then we built synchrotrons, which were already the size of a big buildings. And then we built the national labs, the Brookhaven, SLAC, Fermilab. And then eventually the US started to build the next generation super collider, the super collider, which in the end was too expensive even for the United States to complete. So the whole world got together to build the Large Hadron Collider, the LHC. And the result is that with these big projects, the data that it takes several decades to acquire and billions of dollars to collect, the data is here to stay for decades. But today there is a new way of doing science. Mid-scale science is emerging. This is becoming the optimum scale of science, because the small-scale science is, you cannot do too large things. The very large experiments are becoming too rigid and too risk-adverse and too slow. And technologically, they have a too large lag time. But if we actually look at today's science, all the funding agencies are starting to actually invest in mid-scale projects, which are in the $10 to $100 million range. And by their size, and also by the organization, they are much more agile and they can stay much closer to the technological edge. And the template is that we create a unique instrument, a microscope, telescope, or a new supercomputer simulation, use cutting-edge technology, take risks, push budgets to the limit, maximize the science, and generate petabytes of data. And they are agile. These projects are agile because of the exponential technology growth. So they have to produce results in a much shorter time than the big science projects. And the only way to do this is to highly automate the experiment. So this is naturally leading to this automated robotic workflows. And this is really the next step in the scientific data acquisition. So it's not just, so one example is, for example, the transmission electron microscope, which feeds its data to an FPGA array, which is sometimes custom built, and that is then feeding to a local storage and so on. Or the Sloan Digital Sky Survey was one of these first examples of the mid-scale projects, and that arose from a public-private partnership. But so what is interesting about this, that there is an enormous fresh creative energy liberated, and this is becoming the sweet spot for science. And the result is that even smaller groups can generate petabytes of open data using advanced technology. And this is also leading to a new computational model. This is leading to an opportunistic computing. So these projects don't want to build their own data centers or their own computer centers. They basically need to capture the data after the first meter. So right next to the electron microscope or right next to the telescope, and they have to ship it somewhere where they can the cheapest computer time available for the analysis. And this is fundamentally different from the way we have been operating, with the CERN data center and so on in big science. So one of the examples is that I had a personal involvement in for many decades is the Sloan Digital Sky Survey that started in 1992, and the Sloan 2 proper finished in 2008, but actually Sloan 5 is still underway. The data is entirely public, open, and free. So at Hopkins, our group built the database, and the project marked the transition in astronomy. We went from manufacturing the astronomy data to mass production. And again, I have to remember Jim Gray, who worked with us for many years to build the prototype of this data system. And we used it to figure out what would data access be in the 21st century. So we set out to use a visual interface, a highly visual interface integrated with an object relational DB. And what we saw, an incredibly fast adaptation by the astronomy community. By today, we have about 10 million distinct users who have been using the database, compared to the 15,000 professional astronomers. And we saw the emergence of the internet scientists who made original discoveries, which led to major discoveries published in Nature and Science. And we also introduced collaborative server-side analysis, essentially cloud computing, several years before actually clouds were built. And scientists in this process, we all had to become publishers and curators of large data. We had to pick up these new skills because simply there was nobody around we could turn to. Astronomy adopted the open data very fast, and I was always curious why that was. And at some point, suddenly realized that we astronomers cannot experiment with stars in the lab. I can't go into the lab and push a button and suddenly a star goes ping on the sky, supernova explodes. All that we can do is observe. And Jim was very vocal about how important it was for him to work with astronomers. So Bill Gates did his annual interview at Microsoft and asked him, why do you spend half your time working with the astronomers? And Jim said that it's very exciting work with astronomers since their data is worthless. So the fact that our data didn't have any commercial value was a distinct advantage. We were able to share it freely with not just Microsoft, but with anyone in the world, really. And this made it very crisply clear that scientific data must not only be open and fair, but it has to be actually free and sustainable. So scientists, we cannot ask for a credit card from an astronomer whenever they want to look up something on our celestial database. And it also, since millions of people are using it, it has to be sustainable because people rely on it. So this led to our institute ideas, the Institute for Data Intensive Engineering and Science, where our goal is to do open science with interactive petabytes. And in a sense, our single sentence mission statement is provide disruptive assistance and learn from patterns and turn the patterns that we learn into processes. And so we are trying to institutionalize the lessons learned from the Sky Server in astronomy and try to translate it to other scientific disciplines. And we saw some of the patterns that science engagements have, for example, distinctive phases of maturity. We need a critical mass of interdisciplinary postdocs and software engineers, where from this pool of talent, the projects can always find the required skill sets to borrow for a few months. And this is the most cost-efficient way for a university to actually facilitate and provide this assistance. And we have currently more than 70 ongoing projects. These are all the projects on the Sky Server, which grew out of the Sloan Sky Server. And we have also now major involvements with national labs. So we have basically as Sky Server install at NIST. We are working with the DOE, with Brookhaven, to have another Sky Server there. Our Sky Server is hosting a lot of NASA data from Goddard Space Flight Center. Max Planck is running a Sky Server for the data system of a German X-ray satellite. The Japanese National Observatory and Rutherford Appleton are also involved. And so currently at Hopkins, we have about 30 petabytes of storage, 200 servers. And much of the 10 million users are, of course, coming from Sloan. But the other projects are also picking up speed actually very, very rapidly. And we are able to operate at very good economies of scale. So through the Sky Server platform, we have actually a good, unique expertise to actually how to help mid-scale projects to handle petabytes of data. Aggregating data is hard. So this is what the Sky Server really tries to do. And this is the main challenge in creating big data sets, is how do we aggregate this data? But it has to be done because very often the joint analysis requires collocation of different data sets in order to cross-correlate. The data items have to meet in a CPU somewhere where we can do the cross-correlation. And one of the common mistakes that everyone is trying to do when they try to fuse and aggregate multiple data sets, which came from different sources, is to create a mother of all databases, to actually tie them very closely together, develop a common ontology and a common data model. And this becomes combinatorically complex because if you already have two data sets that you tie together, you bring in the third, you have to tie it to both of those and so on. And it becomes basically a quadratically complex problem. And generally, our philosophy has been to keep it simple and try to establish a linear complexity, which means that when we bring in a new data set, all these data sets have to be a standalone, well-documented, well-tied down database, which has to be self-consistent. And then we bring these in and into a common environment where these data sets can be actually cross-correlated, but we leave it to the users to actually do some of these cross-correlations, but we give them the tools to be able to do it. The users can have their own databases and scratch storages to basically create value-added aggregation and store the links. They don't have to copy data out of the context. They can actually just store the links to the pointers to the corresponding data pairs. And this worked remarkably well. People actually adopted extremely quickly. And we allow the users to share all these value-added data sets, these to be shared, and these are always actually intermediate data sets as well that lead to that are part of a progress towards a paper. They can share it with the collaborators at the owner's discretion. So we have basically different, similar to the Unix access privileges. We also have some data sets which are world visible. And we can, such a way, we can add new data sets and modalities in isolation very quickly, so we achieve a linear complexity. So we can really have many petabytes of data, and we can support the data-intense collaborations. So the lessons learned over the years is that, first of all, statistical analysis and collaboration and aggregations of data are much easier done with the database than with hundreds of thousands of flat files. And it also ensures a referential integrity. It's much harder to lose the data if everything is kind of tied down and checksum then backed up. The collaborative features are essential. And the people grew very quickly beyond SQL. So people actually use SQL like a musical instrument, like a violin, and they played beautiful music. But the point came that beyond the aggregations, they wanted to do deep learning, they wanted to Python scripts. So basically, it naturally integrated. So we integrated the system with Jupyter and various deep learning toolkits. We found that almost everything is spatial, so spatial features are very important, and this is again where database indexing is essential for a fast access. What we saw that almost in every project there was no single access patterns. There was always a hierarchy of different access patterns, from interactive visualizations to interactive small-scale analysis to large-scale scale-out batch analysis. And so therefore, we had to store the data in such a way that each of these access patterns were equally possible. Automation, even in the data acquisition stage, automation is absolutely essential for the statistical reproducibility at scale. Whenever humans are involved, they make decisions, and this makes the data set uneven and not necessarily reproducible. The scale out was much harder than we ever thought. So simply, moving data on petabyte scales is actually very non-trivial. We always have to keep deep links to the raw data files. We cannot ever discard them. Imagine that we discover a new phenomenon in the highly polished shrink wrap data. We have to be able to go back all the way to the raw files to make sure that this is not an instrumental artifact. Another deep lesson was that we had to find a common uniform processing level that is good enough for the community. It may not be the best in every part of the data set, but it is uniform for statistical reproducibility, and keep it stable so that we can earn the trust of the community, which takes time. It takes several years to build up the trust in a community until people actually start using your data. And basically, moving the petabytes of data is hard, so we had to go to extreme ways to figure out ways of smart data caching. And the important thing here is in all of these things, we have to find the right trade-offs. Don't try to do everything for everybody, because then you will fail. So how can we turn these lessons into practice? We saw many repeating patterns in different domains, which were really just the same. And we are now trying to turn it into processes. And there is the first trade-off is right there, is how do we protect the valuable data to make sure that people can't change that, can't tinker it, and can't delete it, while we allow the creative innovations. And these are where the main disruptions come from. And basically, we try to do this with this two-tier that we have the data contexts, which are read-only, and on the surface of this, the users can do anything and everything in their own databases. So this is how the creativity meets basically the stability and reliability. We had to invest a lot in critical sustainable human infrastructure, where we found that there are a few key roles. There are the architects, who are senior people who can talk as equals to the scientists in the projects, and they can translate their problems into architectural solutions. Then we need the implementers, a whole pool of different talent skills or technical skills who can then build the prototypes and build actually a production copy. Then once the system is built, then there come some very talented young faculty who are very eager to do something new, and they are the one who come up usually with disruptive applications using the existing system. And then we need the trainers who can actually teach the graduate students and so on how to use the new tools. And we need to create a sustainable model for the data and the compute infrastructure. And we have to find the right balance between local and cloud resources. And this is dynamically changing and will be changing for the next decade. And we also need to create an active support in the creation of novel data resources and databases. And we have to innovate in the data collection. I will talk a little bit more about this next. But all of these require ongoing commitments from the host institution, not just one-shot investments. So these are, some of the leapfrog projects we created, which grew out of Sloan. So we created in 2006 the turbulence database, where we collected the world's largest turbulence simulations from Argonne, Oak Ridge, Los Alamos. And we created a virtual observatory of turbulence. Today, it has about 1.5 petabytes of data, and it uses immersive sensors. People can take a laptop anywhere in the world, and they can basically insert tens of thousands of test particles, virtual sensors that can measure, for example, dissipation or fluid velocity, and send back a data stream to the laptop from the simulation in the box. And today, we are over 200 trillion points that we delivered to the world, and this resulted in hundreds of papers. We started out a few years ago. Skipped over. Yeah, a few years ago, we started out on building a 1,000-fold increase in imaging data for cancer immunotherapy and build a large spatial database, essentially the equivalent of the Sky server for cancer cells. And today we have, processed more than 16 trillion pixels, and we have over 500 million cells in our database. And recently we started out on the Poseidon project, where we are building together with MIT and Columbia, the world's largest ocean circulation model, with 2.5 petabytes data is on the way, but it will be interactive. We will be able to do interactive science with 2.5 petabytes. So, and these are all mid-scale projects. That is the interesting thing. So these are all built by small teams of people. So just a few examples, from stars to cells. Basically, there are strong parallels between medicine today and astronomy 25 years ago. And the stars and galaxies are the atoms of the universe, and the cells are the atoms of the tissue. And we all have to do, in both cases, multicolor photometry, image segmentation, data locality. And we have to look at the spatial relations, for example, how the tumor and immune cells interact. And we are transitioning to the Industrial Revolution, and we had to rebuild the whole workflow. And this is, I think I skipped over, this is a collaboration with Jenny Staub from Johns Hopkins. And essentially our goal is to increase the data acquisition by a factor of 1,000 by using both a pool of microscopes and also a very automated software pipeline. However, so basically just to mention, actually we are today at 22 trillion pixels that process. The whole Sloan Digital Sky survey was 7 trillion. So we are basically, our data set currently required already 3 times as much processing as all of Sloan. And this shows a workflow which still has a couple of places which are basically involving a human. And we need to get rid of those because they are standing in the way of the further scale out. But much of the workflow is actually massively parallel, as shown basically from this parallel. This shows that many of these tasks can be executed parallel on the slides, for example, for a given clinical study. Okay. How can we measure the usefulness of data? There are 3 pieces to this: the cost, the value, and the price of the data. And wouldn't it be nice if we could translate it into a common denominator so that we can make rational decisions? And what is the value of data? It is clear that it is the direct foundation to many publications, provides the basis for reproducible science, accelerates testing ideas, and so on. And how can we translate this into dollars? And so a typical NSF astronomy grant is about $300,000 over 3 years. And if they publish typically a paper a year, this means it's about $100,000 of research money spent on producing a paper. So that's a ballpark figure. It's not 10,000 and it's not 1 million. So the bottom line here is scientists spend $100,000 of their research money to work on a data set and produce a paper. So every paper is published that is using foreign data is a $100,000 vote on the value of a data set. What is the price of scientific data? How much did it take to build and run the experiments? Typically spent over a decade during the lifetime of the experiment, and there's about a 50-50 split between construction and operation. So a new electron microscope is somewhere between 10 to $50 million. The Sloan Digital Sky Survey started out at 25 million, but over the years it grew to 200 million. Rubin LSST, the LSST project will be a little over $1 billion. And the CERN LHC, Hubble and James Webb are all over $10 billion each. So all that remains for this investment at the experiment is the data. It's important. And what is the cost of scientific data? The cost is maintaining and preserving the data, and this is mostly in people and not the disks. And so far, so good, while the data is owned by the live projects. But the experiments will be shutting down. And these are the disks the disks, replacing the disks is easy. These are the disks that we had to replace over the lifetime of the Sloan project. That's 1.1 tons of hard drives. But this was the easy part. But actually, since we are offering the data through smart services, the operating system changed, all the software changed that we had to operate with. So all this required a constant maintenance, a constant evolution, and a constant overhaul. But what happens to data when the experiments are shutting down? Who will remember what it is? Who will take ownership of it? And who will pay for it? These are unsolved questions that we have better start addressing. There must be a trusted intermediary between the data and the scientists. And in scientific publications, we used to throw our papers across the wall, across a paywall, to the publishers who actually took care of it for us for a fee. But even that model is starting to become untenable. But what happens to the data? And so if we compare these components for the Sloan, the cost for Sloan of maintaining the data is about $500K per year. It's mostly, a good part of it is in people. The value is in $100,000 per paper, and the price that we paid to acquire the data was $200 million. So if we compare this, we actually published over 10,000 published papers were published on Sloan. And that has essentially, based upon this metric, it has $1 billion value. So this compares favorably to the 200 million. But also basically the 100K per paper. So if the archive produces 5 papers a year, then pretty much it already is on par with the cost. But if I compare it to the price of acquiring the data, sustaining the data takes about 0.25% per year of the cost of the price of the data. So 5% of the survey's price would cover the data for 20 years. And these numbers are actually quite typical for other projects. I actually did the numbers for Rubin and for other things. How can we future-proof the open data? If I asked you, do you have enough data or would you like to have more? I don't think anyone would actually answer, I don't want to have more data. But that's actually the wrong answer because the question was ill-posed. I didn't specify what kind of data would you like to have more. And generally, by dumping just more data at your doorstep doesn't make life easier. Sometimes it's much harder to sift through actually a lot of garbage. And what you understood from the question implicitly, even though it wasn't there, that I would like to have more relevant data that improves my science. And so there is, as we are going increasingly more parallel and pulling together and aggregating more and more diverse data sources, the big data is usually synonymous with dirty data. And so we have to sift through more and more of the garbage. And there is also a delicate trade-off between the scientific value and the cost of collecting and preserving the data, of the incoming data. On one extreme, if we store everything, capture all the data bits, we go bankrupt and spend all our budgets on just the data collection. And the other extreme is collect too little data and then we don't have enough for the science. And the LHC provides a very important lesson, the Large Hadron Collider. So basically the challenge is to find, on the detectors, they get zillions of events. So this is like finding the needle in the haystack problem. But the problem is that they don't know what the needle looks like. So they have to basically find the hay and eliminate it. So they are using in situ hardware filters, which basically find the hay in the incoming particle stream and they throw it away and try to carefully preserve those that may be leading to unknown science, the detection of unknown particle. And as a result, they only save 1 in 10 million events, and the remaining data set, that this small subset that they collect, is still 10 to 100 petabytes. But the trade-offs are essential. Maybe, the particle physics, this number, the 9 or 7 nines is extreme, but everybody will have to do this sooner or later, to do a 9 to 1 down select or 99 to 1 down select or 999 to 1. That's up to depends on your problem, but everybody will have to do some trade-offs. So we have to collect more relevant data. And so we need to dramatically improve our experimental design. And this is where AI comes in. And we are today comfortable in using AI after we collected the data and analyze it. But we have to use AI before and while we collect the data. And it's already happening at CERN and material science, drug design, and in astronomy. And maybe this will be the 5th paradigm, where the algorithms control our experiments and they make intelligent real-time decisions in a feedback loop. And this is a project that is funded also by the Schmidt Futures, that we are trying to build an algorithm that works with the PFS, the Prime Focus Spectrograph project on the Subaru telescope, in selecting targets basically in an optimized fashion in a feedback loop, where the algorithm is actually refining the target selection within certain limits. And so if an AI algorithm, the take-home message from this, if we trust an AI algorithm to drive our cars, why cannot it run our microscopes and telescopes? And soon, my premise is that soon it will. There is another aspect to AI, the agility versus tenacity. How can we compete? And basically, we see extremely agile changes in the industry, particularly in AI. So in Google, Jeff Dean's group started with 15 people, and then in a few years, it grew to 15,000. And one cannot imagine such a dynamic growth at any university or even any national laboratory. It's only possible in the industry. So we cannot simply compete with that. And typically faculty hires are for 40 years. So this kind of sets the time scale for dynamic growth at the university. But we can compete in tenacity and high value data. So basically, it's easier and easier to create mid-scale projects at universities, which can generate petabytes of very high value data, which have they can also collect very relevant data using the right AI technologies. And the innovative uses of AI will optimize the experiments, but also the analysis afterwards will discover new patterns. But this requires also the data sets to be AI ready from the beginning. But this is also not enough. So it turns out that the breakthroughs will always come from the new scientific major breakthroughs will always come from a unique data set. There are many, many examples, but it has to be also combined with a disruptive idea. So we need actually the young and smart people with fresh ideas who actually can use the tools and the AI tools and basically then can derive completely new insights and come up with approaches which completely turn the field upside down that everybody will follow afterward. And the way we do the data analysis is also changing. And like it or not, this is happening. And if we look at the music industry, I used to buy LPs and CDs. And the model was I went down to Virgin Records and bought basically the Miles Davis LP, took it home and played it on my record player. Then came iTunes, which revolutionized the world because it was a digital copy. It was an MP3 file. I still had to pay and buy my own digital copy of a song, but I didn't have to buy the whole record. And I still had to download that song and play it on my own MP3 player. And then came Spotify and Pandora, where everything happens in the cloud. I don't even know that which song is coming in what format down to my player. And I don't have to select the individual songs, but basically everything happens in the cloud. What are the data equivalents? We used to send tapes. We used to send disk drives. And later on, when the data became larger, we sent server boxes full of disks to transport the data because the networks were just too slow. And we analyzed this at home. Then came the SQL archives, like the Sky Server or a lot of the astronomy archives, where we didn't have to download the whole data set. We could actually we could write a SQL query that was taking a chunk of the data, okay, and we could download that chunk, essentially one song at a time that we needed for the paper. And with Google Colab, and this is where we are heading with the Sky Server, that everything happens up in the cloud. And so as a result, we will need to start changing our scientific software that needs to be analysis ready and cloud optimized, which means that it has to be basically ready to execute anywhere. And with the containers, Docker containers, and the Kubernetes, the computing environments are changing, and the differences between a campus computer and the national supercomputer and the Google or Amazon cloud are slowly starting to disappear, but there are still substantial differences. And a lot of the scientific codes of today were still written in Fortran 70. So we need to start actually addressing this challenge. How can we make our codes ARCO? Bottom line is many of these challenges are not technical, but they revolve around the data lifecycle and the service lifecycle. The value of our national investment in science, the hundreds of billions of dollars spent over the last few decades on science, is in the data that we acquired. And these high-value open data sets will live for decades. And this is true not just from the big science projects, but also today mid-scale projects are producing petabytes of high-value data that needs to be preserved somehow. We see already much more data reuse, but for the data reuse requires also that the data should be free and sustainable. But there is also a service life cycle. The data is becoming smarter. It's provided by smart services, and these platforms need to be maintained for decades when the computational paradigms are changing every 2-3 years. So more slow and the Kreider's law and all those laws still equally apply to the services. So smart data platforms are constantly evolving. They are following the technology. So what is the economics of long-term data? So basically these $100 billion investments are a national treasure which must be preserved. There is a conflict though. The short-term federal funding cycle prevents the funding agencies to make typically long-term commitments. So whenever this issue comes up, they hide under their desks. And the different federal agencies have different strategies about this. So NASA actually has long-term data centers. NIH is trying to build the data commons. But basically, the NSF MREFC is trying to build a data center for the different projects. Also, that is starting to slowly change. DOE national laboratories are again trying to do it on their own. there is no general strategy, whereas other countries like Germany are creating this national data, research data infrastructure, which is cross-cutting across the whole German government. But when we look back, the Smithsonian is hosting physical specimen from historical scientific discovery, and it emerged from a private-public partnership where the original seed funding came from Smithsonian, and then it was augmented by the federal government. So where is the Smithsonian of data? We need something, sort of an independent institution that cannot be scratched out with the stroke of a pen. It is also fault tolerant and has no single point of failure. So the challenges that we are facing are primarily non-technical. We see that there is this enormous shift in science. Today, everything is becoming data-driven. The organization of science, the granularity is changing. We see a new model emerging, the mid-scale. This is also changing the relationship between scientists and data. Scientists have to undertake more and more curation responsibility because the publishers are not going to do it, or if they do, then they do it for a fee that we cannot afford to pay. We need a trusted data intermediary which empowers sharing and reuse, and the future is automation is the key. AI will be everywhere. Open data is a wonderful legal framework for sharing, and it has made a tremendous progress, but scientific data needs not just fair, but it needs to be also free and sustainable. And the big dilemma is funding and coordination. And so we need a new national strategy for preserving open data that will lead to better open science. And this is an ocean of data that we see on this picture, and this is a sunrise. So this is just starting. Thank you very much.
Alex, that was fantastic, and I hope the young, brilliant researchers in the room will take the challenges, the many that Alex has put before you. We have about 10 minutes for questions for Alex, and Alex will unfortunately not be with us later or at the event tomorrow morning, so here's your chance. There's a microphone here. Raise your hand, please, and surely there must be a question. Don't be shy.
I'm coming.
Hi.
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 Say who you are and a little bit about your area.
Yes. So my name is Bing, and I'm a first-year master's student majoring in industrial engineering. So my question is, as you mentioned about the data collection part, you said in the future we might use AI to build a better collection part. I think currently, because the data I'm working on is very messy, and also I feel like it might be a very efficient part during the data collection. Could you explain more about like how is that possible to use AI to make the data collection part more efficient so that the data is cleaner?
So what is your area of science, if I may ask? Material science or?
No, it's industrial engineering. So
Industrial engineering.
yeah.
So basically, you know, whenever you create an experiment,
Yes.
then you have many choices. Okay.
Yes.
And the goal of the experiment is to measure some quantity.
Yes.
And you don't start out with zero data. You already have, so you are somewhere, you know, a third of the way through the experiment. You already have some data.
Yes.
Then you always have to some choices. You know, what part of the parameter space do I want to collect data from?
Yes.
You know, and then the question is, you can choose this randomly, so you can choose a completely random sampling.
Yeah.
That I just want to cover all of the parameter space, but you can already create a feedback loop, so-called active learning,
Yes.
where you take that, given the data that I already have. This gives me already some constraints on the quantities that I want to measure, but which part of the parameter space has the largest or contributes to the largest uncertainties? How can I objectively select then points from that part of the data space, of the parameter space, that would give me for the given, let's say these are expensive experiments. So every experiment I do costs $1,000. How can I select, how can I best spend my next $10,000 to basically optimally select the best data point that gives the largest improvement in my parameter fit to the data?
I see. So basically you select the variable you want to investigate on, according to AI, so that you can save the cost, right?
You try to basically estimate the uncertainties in your model given your data.
I see.
In your model of the process that you want to acquire. And of course this is called active learning, and this has been around, but applying AI to this would be actually revolutionary.
I see. Thank you.
To this feedback loop. Yeah, you're welcome.
Thank you.
Okay, thank you. I would invite those that are joining us remotely to send a question and then I'll ask Jing to read the question if they send a comment to the host of the virtual site. So if we're, let us know if there's some comments coming in with questions. Any other questions? Yes, here we go.
Thank you for your talk. So I'm Nathan. I'm an AI and science postdoctoral researcher. And one of the things that you mentioned that I find really interesting is talking about how we can make data science open and available for everyone. But my question is, how are we going to achieve this when technology isn't ubiquitously distributed across all regions and to all people?
So this is a hard question. And furthermore, this is also an area that is evolving very, very rapidly. So whatever you learn today, it will be obsolete in 2 years.
Yeah.
So how do we do this? I think the traditional linear learning models at universities are not going to work. We need something more like a snowball effect to train the trainers, in a sense. Work with a bunch of good graduate students, and walk them, help them, teach them AI techniques, for example, that they can use in their PhD thesis, but with the caveat that in exchange they will have to go back, for example, to their own department and teach the other graduate students who have similar type of challenges, who are kind of fitting the same template, and so on. So to create somehow an exponential runaway process, and of course we have to start also, these big data science classes should be kind of taken by everyone, and the sooner we start this, the better. Because later on, when you are already midst of your career, there's no time to actually go really deep in a new area. But if you are actually achieved a certain depths early on, then you can keep up with the changes, and then you know where to look, where to look for new material and how to learn.
Okay, great, thank you.
We have time for one more question.
So, hi, my name is Vita. I'm a senior undergraduate student studying nuclear engineering. And so I was going to kind of jump off of the previous question, which a big thing right now in the nuclear industry is data is very secure and it's not really open source at all. So how do you suppose you're going to motivate industries and companies and national labs to actually share their data when it's a matter of security or like money, essentially? So I was wondering if you might be able to speak to that.
Yeah, this is hard, but in a sense, this is what medicine and health sciences have been struggling with for the last few decades. And this is HIPAA, the personally identifiable information. And basically the only way around this is to create essentially a safe space for the data, an integrated environment like a cloud environment, where the access is controlled, but all the data within that space is actually shareable and accessible.
Yeah.
And we are involved in a similar project at Hopkins where all the medical data is taken out of the medical data system called EPIC, and then we basically create a carbon copy in another big database that is modeled after the size server called Cruncher. That's a secure version of the size server. And you can access this only through a smart terminal interface, which doesn't allow you to copy out data without a permission. But you can actually do your integrated data analytics actually inside this environment. This is effectively what is also happening, I think, in the national laboratories on the other side of the fence.
And that database, that health science database, is HIPAA compliant? Viewed as HIPAA compliant?
Yeah. That's absolutely,
Yeah. Well, thank you so much, Alex. This was a terrific talk. Let's all give him one more round of applause. Before you leave, it's my Ying. We've recorded these, right? And you're going to post them. So I expect many of you had the same feeling I did, that somebody I know should be hearing this talk, right? Maybe your advisors or so forth. So watch for them, and all the talks will be there. But this is really Where the World of Data is a talk done by the man who's done it. So thank you so much, Alex, and I'll look forward to getting music from you. Okay, bye-bye.